Hi everyone, welcome to the third session of the Program Evaluation and Intervention Studies course. In week 3, we're going to look at our first type of causal model, and that's the differences in differences regression models. And so let's begin. For our meeting today, for our agenda, for the first 5 minutes, we're going to have a welcome and session overview and we're going to identify the session objectives. We're going to discuss the importance of research design by improving regression models. We looked at a lot about regression last week, and so this week we're going to show some other modifications that we can make that can help improve the validity and accuracy in our results. And our first part of our discussion is on differences in differences. We'll introduce causal modeling and differences in differences models. We'll discuss assumptions and improvement over standard regression, and we'll review the concept of the counterfactual. The second part of the discussion, we'll look at regression case examples for differences in differences. We'll demonstrate DID examples, use the R package HAM, demonstrate how to interpret results, produce graphs to visualize results, and review how to assess the counterfactual. And in the last 5 minutes, we'll wrap up and go over our next steps, where we'll outline steps in preparation for the next session. Okay, so let's begin with differences in differences with our background. DID developed as early as 1850s by John Snow, proving that contaminated water was a cause of cholera. And we had more improvements in the method later on in econometrics. DID is a quasi-experimental design with treatment and control groups to obtain an appropriate counterfactual to estimate a causal effect. And on the right side, we see the a section we've looked at in past sessions. This is the untreated control group design with dependent pretest and post-test examples. And if we look down at that table in the bottom, we see that we have 2 non-randomized groups. On the top, we have 2 observations with the treatment in between, and we call that our treatment group. And the group on the bottom has 2 observations but no treatment, and we refer to that as our control group. Observation 1's are pre-test, and observation 2 is our post-test. And NR on this table means non-randomization in our sampling. DID is typically used to estimate the effect of an intervention by comparing the changes in outcomes over time between a population that is enrolled in a program and those that are not. So we can use it to get our intervention effect. Here's some more on differences in differences. This is a DID estimation with a graphical explanation. We see on the left side we have a graph showing progress. The red solid line that we see is for our treatment group, and that blue vertical line that we have in the middle of the graph represents the treatment period. So on the left we have our observation or pretest. On the right we have our post-test observation, just like we see on this table on the bottom right. So we're seeing that this research design is matching these results. We have the treatment in the middle. The red line represents our treatment group. The green line represents our control group. And what we see in that red dashed line represents our counterfactual. And this is what we get from having a control group in our research design. It gives us the opportunity to get a counterfactual. And that counterfactual is what could have been. So if we hadn't had our intervention, that red dashed line represents the trend that we could have seen without our intervention group. So when we do our regressions, That difference in differences result represents the difference between our counterfactual and our observed treatment post-test outcomes. So you see that highlighted as the intervention effect in this graph. So in differences, we compare trends between the treatment/intervention group and the control group. That's our untreated group. If the trend changes substantially after the treatment begins, it's supportive evidence of our program. Trends can begin going up, down, or flat. The shift in trends is key. So we want to know how that trend shifted, and we want to also know how our treatment group's trend compares to our control group's trend. And we, believe it or not, we have an example of something that reached the Supreme Court. Our KP example of where DID could have helped. And this deals with what are called off-label benefits. Pfizer made claims of other benefits from the epilepsy drug Neurontin. KP used it for these other health problems. In 2013, the U.S. Supreme Court left intact the 2010 award to KP for $142 million. And I have the link there. The issue was that Pfizer correctly reported a variety of improved health outcomes, but incorrectly attributed it to Neurontin. Non-treated patients also showed improvement. Therefore, Neurontin had no effect. Our solution could be to compare trends of treatment and control groups. Observational data methods used since the 1990s won the 2021 Nobel Prize in Economics. There was separate work done by Ingris, Card, and Imbens. These links that you can look up are from the Nobel Committee, and they discuss there's a spelling error on Nobel, but it's the Nobel Prize Committee, and they discuss the benefits of the differences in differences method, and they highlight and comment on the fact that it's been a consistently good method since for these authors since the 1990s. They've consistently shown the benefits of this type of method, and it really helps answer those causal effects kind of questions that we get all the time. The conclusion is that comparing the trends of both groups could have immediately saved KP, Pfizer, and patients from bad use of data. They didn't have a control group, and so the results were misinterpreted as showing a positive benefit for many things that the Neurontin drug wasn't intended to be used for. And so we're going to talk about interactions again. An interaction between two variables implies that the effect between each variable depends on the value of the other variable. The effect of gender depends on age, and the effect of age depends on gender. Interactions between dichotomous variables, variables with just two levels, can be interpreted as a difference between a difference. In other words, a coefficient is a regression for an interaction variable is the difference in means. The differences in differences method uses this interaction to do causal modeling. So when we're using just two dichotomous or binary variables, if you do an interaction between those two dichotomous variables, what you're left with is the difference in differences. And so that fits perfectly with the type of question we're asking and the research design that we're using. There are various assumptions that go with differences in differences models. DID requires that first, the intervention is unrelated to the outcome at the baseline. That may be that one we probably always are, not always, but we almost always are mindful of, because we probably aren't going to assign our best performing patients to the intervention or control group. If you're in a hospital system, it's usually up to the hospital whether they want to decide to use a program. So if you're the leaders in the hospital system, you may not even be able to assign these kind of programs to hospitals themselves. It's usually up to the hospital. It's a separate entity, generally speaking. So if they want to participate in the program, they can. They may do it because they feel that they need to improve, but that wouldn't necessarily mean that they're the highest or lowest performing medical centers. It could be just an absolute decision, not a relative decision of whether they want to perform. They might not perform because they're on the lowest end. They might lean that way, but ultimately it may be a decision based on other things. So this intervention related to the outcome at baseline, that one is usually something that that's less of a concern. The second assumption is that treatment and control groups have parallel trends in the outcome. The third assumption is composition of intervention and control groups is stable for repeated cross-sectional design. What we're going to cover today isn't a repeated cross-sectional design. It's just a single cross-sectional sample. But when we do have a repeated cross-sectional design, we want to make sure that our controls stay in the control group and our treatment patients or treatment centers stay in the treatment group. We don't want to see them swap places every other observation period. But again, we're going to look at a pre and a post test only, so this doesn't really apply to us to that much, or it would be unlikely for us to see that. The parallel trend assumption is the most critical of the above assumptions to ensure internal validity of DID models and is the hardest to fulfill. It requires that in the absence of treatment, the difference between the treatment and control group is constant over time. So in other words, we might have two parallel trends going month after month or year after year, and we're going to assume that those two parallel trends are going to hold up, or would have held up if we didn't implement some new treatment or some intervention. And for a lot of things in health, for health outcomes, we usually do see that those trends hold up. Things with low rates, outcomes like 30-day mortality, those might remain constant year after year. That's just an outcome that none of us can avoid. And for most places, our healthcare remains as safe as it was in the previous year. So there are times when we may not have parallel trends, but where we're going to assume with our differences models that without the treatment, our intervention group would have held a parallel trend with the control group. Although there is no statistical test for this assumption, visual inspection is useful when you have observations over many time points. It has also been proposed that the smaller the time period tested, the more likely the assumption is to hold. So that may be an option of when you come across non-parallel trends, that you may want to reduce the time periods you're looking at. Ultimately, if you only have 2 time points, then you'll always have a straight line. So I think that may be the assumption that a trend line with the shorter length may provide more parallel trends. Okay, so in this slide, we're going to look at the strengths and limitations of differences in differences. For our strengths, it's an intuitive interpretation. We'll see in the graphs ahead that, especially when you're looking at just a pre and a post test, that we can just kind of easily get a good feel for what the results are based on that. And the results, when we review what the summary statistics represent, it just kind of makes sense when we're reviewing that. Another strength is that we can obtain the causal effect using observational data. That's a really strong that's a really strong feature of it, is that and the reason we have that is because we're using a control group. So in the Shadish, Cook and Campbell book that we reviewed in the first session, they really highlighted the importance of having greater validity by having more than one time point and having more than one comparison group. So when we have that control group, there's a lot of power in that. We get a counterfactual, and from our counterfactual, we can calculate an effect size or a causal effect. Another strength is that we can use either individual or aggregated data. So oftentimes when we're looking at studies, we may only have data available at the aggregated level. So we may only have data for our hospitals or departments by month. If you've seen dashboards or scorecards, you usually just get maybe the last year or two of data. So you might only have 12 to 24 data points, and maybe more if you're lucky. And so you might just have that many rows in your data set. And so it's collecting data is always a complicated process, and it is very time consuming. So that's a really strong feature, is that we can use either individual, for example, at the patient level, or aggregated data, for example, at the department or hospital level. Another strength is intervention and control groups can start at different levels of the outcome. DID focuses on change rather than absolute values. For example, if I'm in a hospital in LA and I'm compared with a hospital in San Diego, we might be at different levels. San Diego might have a higher performing or it might have outcome levels that are better or higher. And so we're not concerned as much about the difference of where we're starting at, or even solely where we end at, but we want to see that change in trends, the difference in trends, the difference between the LA trend and the San Diego trend. So we can start at different levels. They could be vastly different or substantial. But what we're really focused on is that shift in trends for our intervention group and our control group. And another strength is that DID accounts for change due to factors other than the intervention. So one thing that it highlights is that other important factors that influence the outcome are assumed to affect both the intervention and control group. One big example could be COVID. COVID happened everywhere. It wasn't just limited to certain locations. The degree to which differed between locations, but if we're looking at some sort of outcome and we didn't have ways to account for important changes, maybe state policies, epidemics, or some other, or financial changes, maybe a recession. If it's there could be many other things that affect our outcome. We assume that it's going to be that it'll affect both the control and intervention group, and if we can assume that, then we can rule out those as part of the that effect, because we're actually looking at changes and trends, so we can we're able to, that help, the DID model helps to rule out those effects in the calculation, because it should affect both the treatment and control group. And another strength is DID is a useful technique when randomization of patients is not possible. We just may not be able to assign patients randomly into our treatment and control group. It can be both impractical and unethical to deny treatment to some patients when we have a program that we know works. There are limitations. It requires baseline data and a control group. It's not really a big limitation, because we really do want that control group so we can calculate the counterfactual. We cannot use if the intervention allocation determined by a baseline outcome. Not common, because interventions usually are assigned to the hospital or the department. We cannot use if comparison groups have non-parallel outcome trends, but those interpretations can be improved with interrupted time series, covariate or propensity score adjustment, and splines. We cannot use if composition of groups pre/post change are not stable. In other words, patient data can't be included if they switch between intervention and control groups. So we just want to have a stable treatment or intervention group and a stable control group. So we do have a list of best practices. For example, we want to be sure the outcome trend did not influence allocation of the treatment / intervention. We mentioned that earlier. That's probably not something that we, if you're in a hospital setting, we probably don't have the option to do that even. It's usually we're assigning these interventions to kind of where they're needed, and it could be just a very complex process to try to assign our intervention and treatment group participants in a different way other than by location. We want to acquire more data points before and after to test the parallel trend assumption. We should review at least 2 periods of pre-intervention data and 1 post-intervention data time point. If we're using repeated cross-sectional data, we want to use the linear model to help with the interpretability, including binary outcomes like readmissions, mortality, and so on. So it may sound odd to use a linear model on binary outcomes, but since we're looking at that shift and change in our outcomes, the difference in trends, it's actually a lot easier to calculate with the linear model than it is with the logistic model. It just, for the sake of interpretability, a linear model works better. And we want to use models like generalized least squares, which can be found in the RMS package by Frank Carroll. We use that for auto correlation between pre and post in the same individual. And that may be more of an issue if we're using repeated cross-sectional models. Probably won't be an issue for the models that we're going to run soon. We want to perform sub-analysis to see if interventions had similar different effects on components of the outcome. For example, we want to compare the intervention with 5 similar hospitals instead of all 15 hospitals. When graphing, we want to use pre and post test value lines for both groups. That's kind of a standard practice, is you just get a pre and a post value for your intervention and control group, and you graph those lines. That's a standard approach to graph your results, and then you can review your regression results. Okay, so now we're going to start on our examples. We're going to look at minimum wage and length of stay interventions. We're going to begin with the Card and Kruger 1994 study. In April 1992, New Jersey raised its minimum wage from $4.25 to $5.05 per hour, while the state of Pennsylvania's minimum wage remained constant. The researchers surveyed 410 fast food restaurants in New Jersey and eastern Pennsylvania, both before and after the increased minimum wage. I'm using a slightly modified data set in the example. So the article results and my results are going to be slightly different, but it's the only data set I had available. Contrary to standard economic theory, which predicts that a higher minimum wage would lead to reduced employment, the study found no evidence that the increased minimum wage decreased employment. This controversial finding is still debated today by stakeholders. So the traditional theory was that if you increase the
from geeksforgeeks.org.
If you increase the minimum wage, then employers would couldn't hire as many people, or they couldn't stay in business long enough after having to pay an increased minimum wage. So that's what maybe the traditional economic thinking was at the time. But with the Card and Kruger results, they found that that wasn't the case. Okay, so let's look at the Card and Kruger minimum wage full-time equivalent results. FTE is the outcome, full-time equivalent employee status. 410 fast food restaurants were surveyed on their the number of FTEs they had in their business, and they did it before and after that 1992 wage increase happened. So on the left side we have a graph that shows the pre and post. It shows the pre and post interview results. So we have the time period on the x-axis. On the y-axis we have our FTE averages. Above 0 we see the pre-intervention results, and above 1 we see the post-intervention average values. And that dashed gray line in the middle represents the treatment. So we have our observation one to the left of that gray vertical line, and we have our observation 2 values to the right of that gray vertical line, which represents the treatment period. So our intervention group is that solid gold line, and our control group is that solid purple line. And we have a counterfactual, which is represented by that that gold dashed line going from left to right. And then I have some dotted arrows or vertical lines in purple and gold that represent the difference between our pre and post periods, just to help visualize how big of a difference that is. And on the right side, we have the interpretations, and both the graph and the interpretations come out of the ham package in R. And so those are just pasted in onto this slide. So let's begin with the intercept on the top right in the interpretations, and we can read the intercept as the intercept represents the mean FTE value of the control group at the baseline period, and that at time 1 that's a FTE value of 19.95. So if we scroll over to the left, we see that the intercept is labeled as 19.95. The intercept always starts with where that purple circle's at. So in the ham package, that whenever you see a circle like that, that represents the intercept. For the next variable, post all, it's the change in the control group's FTE value in the second time period, and that's time 2. There was a non-significant decrease of the control group at time 2 for a value of negative 2.41. So if, that purple line represents the control group. So we're going to scroll over to the right on the right side of that graph, and we're going to see that the variable name is post all, and we see that negative 2.41, and we can tell that it's a change in the control group's FTE value in the second time period. So we see that for our control group, the FTE level dropped by about 2.4 points, and you can see that dotted purple line represents that drop of 2.41 points. That's marginally significant. We see a plus sign next to that 2.41. If we scroll down to the that bottom note for p-values, we see that a plus sign represents a p-value less than 0.10. So it's not significant at the alpha level of 0.05, but we can say it's marginally significant because that p-value is less than 0.10. Okay, so let's move on to our next variable, which is int.var. That's the intervention variable, and it's the difference between the intervention and control group at the baseline period. The intervention group had a significant decrease in the mean FTE value compared to the control group, and that difference is negative 2.88. So we're comparing the intervention group and the control group at the baseline. So we'd see that in New Jersey they actually had fewer FTEs on average, and we see that they have about 2.9 fewer FTEs on average. So already New Jersey is starting at a point where they have fewer FTEs prior to the minimum wage change. So this is maybe early 1992 or maybe earlier. And we see that Pennsylvania has that level of 19.95 FTEs, and we see that New Jersey has about a little over 17 FTEs. And then so now we want to look at that difference in trends and that variable DID, which you see on the far right. That actually represents our differences in differences model effect. And so DID estimates the average treatment effect on the treated group, the ATET. This interaction represents the difference in the trend differences for the intervention and control group. So what we're doing is we're going to look at the intervention time 2 value minus the intervention time 1 value, and we're going to compare that with our control time 2 value minus the control time 1 value. And the difference between those between the intervention and control trend equals 2.91, and that gives us our difference in difference effect. In other words, there was a non-significant increase in the mean FTE trend by 2.91 for the intervention group. It's marginally significant, as we can see on the middle right. It has that plus sign, which represents a p-value less than 0.10. So it's not statistically significant at the alpha level of 0.05, but it's pretty close. However, with this study, we wanted to show that there wasn't a significant decrease in FTEs as was predicted by classic economic theory. And in fact, the value increased. The trend's mostly flat, but we do slightly see improvement. When we look at these values that are in blue, on the bottom right, we see that at time 2 is 17.57 for the average FTE. And you compare that with time 1, that's 17.07. So they're relatively about the same, but you can see there was a shift for eastern Pennsylvania. And when we look at the graph, we see that if there was a difference, if there was no difference between if we weren't expecting a difference because the program didn't work, then the trend we'd expect to see with for New Jersey would follow that gold dashed line. We'd expect to see that our FTE levels closer to about 15 or below 15, but in fact it actually increased. So some explanation of why that might have happened is that higher paying jobs may have attracted more candidates and may have also meant that the people who have these jobs were more likely to keep these jobs. They wanted to, there was some expectation that with a higher paying job, it may provide a greater incentive for maintaining employment. So that may have had an impact that wasn't accounted for by traditional theory. So we see that without that control group, we might have had a flat-looking trend. Without the control group, there may have been criticism that there was really no impact, or the impact wasn't immediately seen. In other words, they may have asked for more data. In healthcare, we might see that quite a bit where, if you have a flat trend, it may prevent a program from continuing because we don't see success or we don't see an impact, or maybe that data collection period might be extended to a longer period. So there's a lot of benefit to having that control group. It allowed us to see that maybe, especially back in 1992 when we're still in a recession, so it's perfectly reasonable that we could have had a downward trend in employment, but we could have seen that trend actually improve in states where states had increases in the minimum wage. So it's a really interesting study, and this is a study that was the basis for the Nobel Prize selection. Okay, so now we're going to look at the inpatient hospital length of stay intervention, and this is the one that's found in the HAM data, and this is actually hypothetical data, but used to show what these trends could look like. So it's not a real study, but follows patterns in other studies. So for the program, the stakeholders and primary intended users tell us about their program to reduce length of stay. As evaluators, we're going to discuss the purpose of the program. We're going to study how the program works, and we're also going to gain insight from our clients to figure out what stakeholders and the primary intended users are most concerned with and what information they would find most useful. So the clients feel that without the program, the intervention group would also likely see higher length of stay. So when we have clients mention what things could look like or could have looked like without the program, they're actually telling us about the counterfactual. And so when we hear about the counterfactual, we want to have a control group so we can calculate that, and a good experimental design to use would be something like differences in differences, where we can make use of the control group to give us a counterfactual, and that counterfactual can give us an idea of what the causal effect is. That, in other words, that in our last slide, the DID variable. We'll test the hypothesis with an interaction of the dichotomous variables, time and intervention. We mentioned earlier that when you have two dichotomous variables and you have an interaction, that interaction represents the differences in the difference for the mean. So by default, we're going to get that differences in differences from our interaction. So we're going to make use of the benefit of having an interaction, and we're going to turn that into a regression coefficient, and that regression coefficient is going to give us insight into the causal effect of this program. And so for the study, we find that simply observing a program's pre- and post-test scores won't capture the program's causal impact. Having a control group helps with other factors that impact length of stay. The before and after comparisons give a better counterfactual. This research method gives us utilization-focused evaluation. So we may be doing a program evaluation, or we may be doing an intervention study, but this type of research method gives us an opportunity to use to more effectively use utilization-focused evaluation. So it's always a great thing to use our research methods to help supplement our program evaluation. If you're doing an intervention study, then this would be a natural fit to use this type of method. And so here are our results. We have our inpatient hospital length of stay. On the left, we have our graph that represents our results, and on our right, we have our interpretations. These are the same graph and results that we saw in our previous example. They come out of the ham package, and so we can see that. And I should restate that I'm using recent revisions for the graph that we see on the left. The interpretations are the same that you get in ham 1.0. The graph is something I've been working on that'll come out in the next version of ham in a couple months. And so I can't do this exact graph on ham 1.0, but I do have some code to help you install that version if you wanted. And I'll show you the standard graph that does come out, and you can take a look at what's in the newer model that's on github.com. And if you prefer one over the other, you can use whichever one you want. So let's go ahead and start with our interpretations. We see on the top right, we begin with our interpretation of the intercept, which represents the mean FTE value of the control group at the baseline period. So we look for our intercept on the bottom left, and we see that mean length of stay for our control group is 3.5 days. We next go to the variable post all, which is the change in the control group's FTE value in the second time period. That's time 2, or 1 on the x-axis. There was a significant increase for the control group at time 2, which is our post-intervention value. So our intervention group is represented by blue, and our solid pink line represents the control group. So we see that it started at 3.5 days, and then we see that the intervention actually increased by, the control group, their length of stay increased by 1.6 days. So they're now up about a little over 5 on their average length of stay. We see that's actually a significant result. And so now we're going to look at the intervention variable, int.var. It's the difference between the intervention and control group at the baseline period. So we're comparing the pre-intervention period for the intervention and control group. The intervention group had a significant increase in the mean length of stay value compared to the control group. So we see that for our intervention group, they actually had a length of stay that was over 2 days higher than our control group. So the intervention group's length of stay at the pre-intervention period is about 5.7 days. So that's a significant difference, as we see with those 3 asterisks. In our note on the bottom are p-values. When you have 3 asterisks, that represents a p-value less than 0.001. So that's a significant difference. So our intervention group is starting with a significantly higher average length of stay. So now we're going to look at our differences in differences effect, which estimates the average treatment effect on the treated group. This interaction represents the difference in the trend differences for the intervention and control group. So just to review what that means, on the left in the formula below, we see intervention time 2 minus intervention time 1. And then on the right, we see control time 2 minus control time 1. And the difference between those two is negative 3.6. So that means that, in other words, there was a significant decrease in the mean length of stay trend by negative 3.6 for the intervention group. So let's go over and look at the right side, which represents the post-intervention, and we see that yes, if we look at that, the solid blue line represents the actual data. The dashed blue line represents the counterfactual, and the difference between the where our counterfactual would have led us at our post-intervention period, the difference between the corresponding point for the counterfactual and the actual difference in difference value, the actual post-intervention value, that's a difference of 3.6 days, and that's also a very significant result. We see the 3 asterisks, which represents a p-value or of 0.001. So we see that's a significant difference, and just a big difference. Whatever the program was had a big effect on reducing length of stay. I don't know if I've seen something that big, but we can see length of stay of our health outcomes and it's not really a health outcome, but in our health-related outcomes, that's one that can be modified. I wouldn't say mortality would ever see such big differences, but length of stay is something that we can modify. Also, process improvement measures. We looked at one like collecting labs. You can see it wouldn't be unthinkable to see big differences like that with process improvement. This isn't exactly a health outcome, but for length of stay, you might be able to see differences like this, but that's a pretty big difference. And so we see that below that formula, we see the actual values. We see for the intervention, they had at the post-intervention period, they had a length of stay of 3.62. If you subtract that from, if you subtract 5.56 and then use the other control values, that gives you that negative 3.6. So, like I said earlier, in other words, there was a significant decrease in the mean length of stay trend by 3.6 for the intervention group. Okay, so now we're to the summary. We find that adding a control group makes a big difference. We can hand calculate results and quickly prove our hypothesis. We can spot success when our programs look like they have a flat trend, while the control group is getting worse. We can demand a control group if you feel it's needed. See the KP in the Supreme Court example. You can use a results slide to help with setting up your graphs and interpreting the results. When you're just doing 2 time points, the results or the interpretations are going to be similar, and the type of graph you would use would also be similar. So you can kind of use that to model the results for your own work. I have an example. I have some sample code to run for future studies. So you can do this analysis in, say, SAS, SPSS, Data, and other software, as well as R, of course. But if you just wanted to use some of the results slides as an example, that will help. You can use the sample code for future studies, so you can stick with R and use that code over and over again to help with your work. Or if you wanted to create an interaction variable and run as a standard regression in R, SPSS, SAS, Stata, and so on, that'll work too. So I do have a Cardin-Kruger example code file. I'm attaching a file if you wanted to try it out in R. Just highlight the code and press Control and then the R key if using standard R software, or the Control and then the Enter keys if using RStudio. The data file is attached to. Here's where you find the ham package. And that second line is my GitHub page, where you can get the current version if you wanted the additional graphing options. And I made revisions to the results graph that will come out later this year. It's available now on GitHub, and so you can look on the left, that's ham 1.0, and on the right, that's the revised ham on github.com. We have the DID study. And you can just see that I could change the width of the lines. I can add those dotted arrows to highlight how big of a difference our results are. I can add in the variable names and a lot of other options. Okay, so here's the code to download the GitHub version for additional graphing options. You would first need to install the package DevTools, and then you can try these 2 commands. First, this failed on my work computer. If it fails for you, see the next slide. Hopefully these 2 lines will work, and then you can just load your ham package. And if that didn't work, you can try these 2 commands. And this worked on my work computer. What you do is you would go to GitHub, download my R package by clicking that code button, and then downloading the zip file, which I have highlighted with that red arrow. And then you would change this file location. I have G stats with Steve and so on, and then there's the ham master zip. You just change it to wherever you saved your file, and then you can run the code. Okay, and that's it. Thank you, and I'll see you soon.